Welcome to our in-depth training on information systems operations, specifically focusing on the critical IT components that form the backbone of modern enterprise infrastructure. As an IS auditor or operations manager, you cannot effectively govern what you do not understand. In this session, we will dismantle the black box of IT, breaking it down into its core hardware, software, and network elements. We will explore how these components interact, where the risks lie, and how to verify they are managed effectively. Let's begin. We start by establishing a high-level view of the IT ecosystem. Information systems operations is not just about keeping the lights on. It is about managing a complex interplay of components. As defined in our domain, we categorize these into hardware, software, and networks. Hardware is the physical layer servers and storage. Software provides the logic, ranging from the operating system to the database management system. The network binds them together. A critical concept for auditors here is integration. As noted in the texts, middleware is often the glue between these components, and it represents a significant vulnerability point if not patched and managed. You must ensure that asset management practices cover all three categories, not just physical devices. This mind map visualizes the component hierarchy we will explore. At the center is the IT ecosystem. Branching out, we see hardware, which anchors the processing power. Software sits on top, driving logic, and networks provide the essential connectivity. Notice how they are distinct yet interdependent. A failure in the network branch isolates the hardware, rendering the software useless. Let's open up the chassis and look at computer architecture. At the heart is the CPU. It uses an arithmetic logic unit for calculations and a control unit to sequence events. A key distinction for auditors is memory. RAM is volatile. If you pull the plug, the data is gone. This is critical for forensic data acquisition. You must capture RAM before shutting down a compromised machine. We also have the system bus, the highway for data. Regarding processing power, we see a shift from single CPUs to multiprocessor architectures. As noted in the study guide, multiprocessing improves security because security processes can run on a dedicated core without being interrupted by user tasks. Finally, distinguish your asset classes. Mainframes excel at massive I/O transactions, like banking, while blade servers offer high-density computing for modern data centers. This diagram illustrates the classic von Neumann architecture. Inside the CPU box at the top, the control unit directs traffic while the ALU performs the math. They connect via the system bus, that central highway to memory and input/output devices. Data flows back and forth. If the bus is saturated, the fastest CPU in the world cannot process data efficiently. Hardware is useless without the operating system. The OS is the resource manager. It decides which program gets to use the CPU and for how long. Crucially, the OS enforces security through privilege modes. Supervisor mode, or root, grants full hardware access, while user mode restricts applications. A common audit finding is users running applications in supervisor mode, which is a massive security risk. We also have utility software disk defragmenters, compilers, and debuggers. These are powerful tools that can bypass security controls and should be restricted on production servers. Finally, understand that software starts as human-readable source code, but is deployed as object code. If you don't secure the source code, you lose control of the application's integrity. This sequence shows the flow of control. The user interacts with the application. The application cannot touch hardware directly. It must send a request to the operating system. The OS switches to kernel mode to execute the instruction on the hardware, then passes the result back up the chain. The OS acts as the gatekeeper at every step. Networking components connect our systems. We distinguish them by their intelligence and OSI layer. At the bottom, we have hubs. Hubs are dumb. They shout data to everyone, creating security risks, sniffing, and traffic collisions. Auditors should verify hubs are replaced by switches. Switches are layer 2 devices. They use MAC addresses to send data only where it needs to go. Moving up to layer 3, we have routers. Routers connect different networks, like your LAN to the internet, and make decisions based on IP addresses. Finally, firewalls are our security guards. They range from simple packet filters to complex application proxies. An auditor must verify that default settings on all these devices, especially routers and firewalls, have been changed to secure configurations. Here is a typical network topology. Traffic enters from the internet through the firewall, then the router. It hits the switch, which directs traffic specifically to the server or workstation. The dotted line represents the risk of using a hub instead of a switch. If a hub were there, the attacker's sniffer could see all the traffic passing through. Data must be stored reliably. We use RAID, redundant array of independent disks, to protect against disk failure. It is vital to know the differences. RAID 0 is striping its fast because it writes to multiple disks at once, but it offers zero redundancy. If one drive fails, you lose everything. Never use RAID 0 for critical systems. RAID 1 is mirroring. It keeps an exact copy. It's safe but expensive, because you buy 2 drives to get the capacity of 1. RAID 5 offers a balance by using parity data spread across disks, allowing you to survive a single drive failure. Auditors must check configuration. Are critical systems on fault-tolerant RAID levels? Also, distinguish between NAS, file-level storage like a shared folder, and SAN, block-level storage for high-performance databases. This visual comparison highlights the RAID logic. In RAID 0, data A and B are split. If disk 1 dies, part of the file is gone. In RAID 1, data A exists on both disks. If one dies, the other takes over. In RAID 5, we see data A, data B, and a parity block distributed. This parity allows the system to mathematically reconstruct lost data if a drive fails. Modern IT relies on virtualization. This technology uses a hypervisor to slice one physical server into multiple virtual machines, VMs. Type 1 hypervisors run directly on hardware and are standard for data centers. Type 2 run on your laptop OS. Virtualization brings efficiency, but introduces risks like VM sprawl, where VMs are created and forgotten, becoming unpatched security holes. We also have cloud computing. Understand the responsibility shift. In IaaS, infrastructure as a service, you still manage the OS and patches. In SaaS, software as a service, the vendor manages everything except your user data and access. Containerization is the evolution of virtualization, packaging just the application and its libraries for maximum portability. The diagram depicts a virtualized environment. The physical server is the foundation. The hypervisor sits on top, allocating resources. It supports VM1 and VM2. Notice that each VM has its own guest OS and applications, completely isolated from the other, yet sharing the same physical roots. Data is the lifeblood of business, and the DBMS is its heart. The most common type is the Relational Database, RDBMS, which stores data in tables linked by keys. A key concept for operations is normalization, structuring data to minimize redundancy. Redundant data wastes space and creates inconsistency. For transaction integrity, we rely on the ACID model. Atomicity, all or nothing, consistency, isolation, and durability. From a security component perspective, auditors check for database views. Views allow users to see only the data they need, e.g., seeing an employee's name but not their salary, providing a critical internal control layer. This entity relationship diagram, ERD, shows a relational database structure. A customer entity links to an order entity. One customer can place many orders, one to many. The order contains specific attributes like order number. This structure allows efficient data retrieval without duplicating customer details for every single order. We conclude with the auditor's role. Managing IT components requires a lifecycle approach. It starts with procurement. Did we buy approved hardware? It moves to deployment. Did we configure it securely, removing default passwords? Maintenance involves patching and tracking changes against a baseline. Finally, disposal. Did we wipe the drives before throwing them out? A massive risk in operations is end-of-life components. If a server OS is no longer supported by the vendor, it receives no security patches and must be retired or isolated. Your audit should verify that the physical inventory matches the logical records, and that no shadow IT devices are connected to the network. This state diagram tracks the asset lifecycle. We move from procurement to deployment, where the secure baseline config is applied, then to maintenance for patching. Finally, the asset reaches disposal. The critical transition out of disposal requires data sanitization to ensure no secrets leave the building with the trash.